Thank you very much for inviting me to give this talk. So I'm close to the Department of Physics. I'm just near the corner over there. And actually, we are doing in our lab physics, but working on the macro physics, so the physics of the planets, and more specifically, because I'm an oceanographer, on the planet Earth. So I will introduce this macro physics problem, introducing you a little bit about the climate system, because probably most of you know about it, but just to remember, and also about what is the main challenge today for these huge systems that seems so simple, but actually so complex that we have really problem in understanding it, and especially in having forecast for the climate of tomorrow. So this talk is a summary of many collaboration, international collaboration through many different international projects, but I will focus here, apart from some results that are issued from these international projects, also from the work of some PhD students and some later in situ project. So in situ means observations of the ocean in the ocean itself. So the Earth climate system can be just seen in these pictures from space of our Earth. So we have the land, the atmosphere, that here is transparent. We can see only the atmosphere through the clouds in this visible image. We have ice, so the cryosphere, and the biosphere, whatever is life in land and in the ocean, and of course the ocean that is covering most of its surface. And this is very important because the ocean is made by water, and water has really tremendous important properties that impact our system in the mid-climate, but also in its actually changing climate. So the climate system, actually in terms of physics, is a transformation of energy. So we receive energy essentially from the sun that is transformed in, so this is shortwave electromagnetic radiation, and this is transformed in longer wave electromagnetic radiation, so heat, that is transferred from one subsystem to the others and essentially give the climate we are living in. So, and this can be seen in some energy budgets as here. So this is the incoming solar radiations that is partly reflected from in the atmosphere from the clouds. We have seen the pictures, but also from the land, essentially from deserts and ice, and the part that is absorbed is transformed in long-wave radiation, and it is transmitted through the atmosphere, but the atmosphere is essentially transparent to the spectrum of sun energy, but is not anymore transparent to this infrared radiations. So it absorbs it, and this is the greenhouse gas effect, and it retransmits that energy that has been absorbed, part to the space and part back to the surface of our planet. So we receive two kind of energy, they direct from the sun, and this that is due to the presence of greenhouse gases in the atmosphere. So these greenhouse gases are the water vapor, and other that are less important in concentrations, but have a very important radiation impact in terms of this. Yes?
What's the unit? What's TOA?
This is TOA is the top of the atmosphere, because the budget is done at the top of the atmosphere, and the unit are watt per meter square. Sorry. So here we have so this back radiation, long wave radiation, but we have two other terms that is transferring energy from the surface of the planet to the atmosphere. One is the sensible heat, conductivity, but also the latent heat, because water evaporates from the surface of, essentially from the ocean, and goes into the atmosphere, and there it condensed and rain. So there are different kinds of transfer of energy. In here, we just need to remember that most of this transformation is done in the ocean, because it's the ocean that covers the majority of our planet, the surface of our planet. So if we take this budget, in the mean, the equilibrium is 0. And so the solar radiation at the top of the atmosphere need to be equally to the outgoing long-wave radiations, the one that is absorbed. But this is not 0 when we integrate it zonally. So we look here through the latitude from the southern pole to the northern pole. So we see that near the polar region, this energy is negative, energy budget, and is positive in the tropical region. So because of this, if we didn't have the atmosphere of the ocean, we would have an incredibly high temperature here in the tropical region and very, very low temperature in the polar region. Why is not that? It's because the atmosphere in the ocean, here is the total transport, and this is the atmospheric transport and oceanic transport of heat from the tropics towards the higher latitudes. So these two fluids that are very different, gas and liquid, are transferring heat, this excess of heat, through the physics of these two fluids towards the higher latitudes to counterbalance this effect and this imbalance. So I will not talk about the atmosphere, but still here you can see that the ocean transport is not perfectly symmetrical from one hemisphere to the other. It's more, is higher and less negative. So it's going less south in the southern hemisphere compared to the northern. And this have a reason that is due to the ocean circulation. So here are two schemes of the ocean circulations. Here, I'm sorry, it is very small, but you can find the major surface current. Here is the Gulf Stream with the Canary Current that back up in a kind of circulation that we called a jar. And here is the North Atlantic Drift, that is water coming from the Gulf Stream and entering in the Arctic. The Atlantic Ocean is very different from the other two oceans because it has a wide opening to the Arctic region. And so it exchanges heat with this Arctic region, and it exchanges also water. So here we can see a three-dimensional scheme of this global circulation that is not just a surface, but is so when it's red, it's at the surface. When it's blue, it's in the deep ocean. So one parcel of water can do all the loop that is really schematic here in 1,000 or more years. I will come back on that. But as you can see, the Atlantic Ocean is really different from the two others because of this opening to the polar sea that is the Arctic. And so it can exchange warm water here that are cooled, and then to balance, because it's a fluid, the incoming water from the south, there is cold water going out and filling the other basin and changing with time from a deep water that is usually cold because it doesn't receive the energy from the sun, and it is transformer and comes up in the upper layers. So these are schemes, and in reality, the ocean circulation is very complex. As I will show you, we do not know yet how complex it is because we don't have yet the capability of really observe all these scales, at least at global scale, and also to model it. But these are the governing equations. So we have the Navier-Stokes equation for conservation of momentum and mass. We have the conservation of heat and salt. And again, the equation, sorry, I wrote conservation of mass, but this is the equation of state for the density for the ocean. And you have theta is the potential temperature. And so in the atmosphere, you have just temperature ruling the equation of states with pressure. Here we have also salinity. And this equation of state, if I have to write you down what it is 2 pages of very nonlinear of a very nonlinear equation in pressure, salinity, and temperature. So because of this nonlinear term, in both the equation of states and the Navier-Stokes equation. So we have really a range of processes that interact all together. Here is a spatial scale towards the time scales of this process. So climate change is put here, so very long, large scale, a very long time periods. But actually, what we are living now is something that is happening really fast compared to what has been past climate change. So, and the problem in our field is to try to connect with knowledge equations, completely different time and spatial scales. So this is very difficult to do with the observations, but also with the models. So we have a problem in a rotating sphere, a fast rotating sphere that really affect the motion, but also we have two fluids, the atmosphere and the ocean, that are stratified. And also this stratification is putting many complexification to the dynamics of these two fluids, and in particular that of the ocean. So now I go back a little bit to the concept of actual climate change. So here are the measures, Mauna Loa, of the CO2 in the atmosphere with his seasonal cycle. And we see that this CO2 is increasing rate, so it's essentially going exponential in terms of concentration in the atmosphere. ppm is part per million. So this is not very high as a concentration, but it's really important to change temperature on our planet. And here are the last measure of March, 407 ppm. Yesterday I watched it, how much we were. We were around 410. So it is increasing pretty fast. So we are here. And this is the mean global temperature measured with a base period on the 20th century from the 1870. So you see that the temperature on the globe is increasing with some variability. This is natural variability of the system, the climate system, and is following the shape of the CO2 increasing concentration in the atmosphere. So now said that, we go back to the pictures of the energy budget. So these are different figures, but the numbers here are more or less the same. The only problem we have is that because of this presence of CO2 gases in the atmosphere and increasing water vapor, increasing methane, other greenhouse gas from anthropogenic origin, we are in a situation that our energy budget is not closed. And we have lost heat in the system that we do not know really where it is, because the balance is not instantaneous. Every transfer of energy takes time to happen. So we are not yet in the balance with this new increased greenhouse gas in the atmosphere. So the question here is, where is this missing energy is gone? So now I'm going to the ocean observing systems. And one of the more efficient systems we have to observe the climate system is the satellites. So I'm talking now about a constellation of satellites that are increasing, some are dying, and what we can see from the remote sensed observation, what we can say about the ocean. So what we can measure? Sea surface temperature. Sea surface temperature has been one of the first measures. We can measure it with infrared or microwave, and blending together different satellite measures, we can have fields that are 1/10 of degree of resolution, and they are daily. They are daily fields. So you can see that the tropics are warm, the polar region are really cold. So these cold color are really cold temperature, and but the the structure of the sea surface temperature is not completely zonal because of the ocean circulations. So here, for example, if we go in the Atlantic, we have the Gulf Stream, and here we have the Labrador Current. So near the American continent, at the same latitude as France, we have colder water than near France and the United Kingdom. So we can measure since essentially 92, the end of 92, the sea surface height of the ocean, and this is the mean value of the sea surface heights, with regions that are in red that are higher, regions that are in blue are lower. In the mean, this is the equilibrium of the ocean, so it's not flat, but has little hill and and a huge valley. And where the color changes is where the currents at the sea surface are concentrated. Since 4 or 5 years, we have satellites that are measuring a proxy for sea surface salinity. So this is one of the newest fields we can have. And so we see, for example, when it's red is saltier, when it's blue is fresher, so less salt in the water. And we see that the ocean is not homogeneous, and the saltier basin here is the Atlantic Ocean. And also we can see with the visible images, we can try to assess the surface chlorophyll, so the biosphere of the ocean, some information on the biosphere of the ocean. And so you see that there are regions where notably you have this red region here or here. They are seems poor of life compared to region in the southern hemisphere, in the Southern Ocean, or because here is spring, it's taken in spring, in the northern hemisphere at spring.
So the height is measured with respect to what?
So here we have more than one satellite and some models to try to have the mean geopotential height and to measure the sea level compared to the mean potential height. It's a measure of the distance from the surface to one satellite that is really well positioned. And since 2000, we have 3 or 4 satellites flying together in order to have enough high resolution for these fields that I will show in the next slide. So apart this field, that is an integrate measure of what is happening in the upper layers of the ocean, all the other fields are really measuring what is happening in the first millimeters of the sea surface. We are not going deeper than that with this image. Yes?
So any reason why there is a depletion of chlorophyll under the tropics?
Sorry? Why there is this chlorophyll?
Yeah. When is it depleted? You would expect more light? Well,
actually, the problem of life is that need nutrients.
Okay.
So when they have nutrients and they eat it, they use it, and if they do not have input of such nutrients, they will die. So this is why in this region properly, for example, right at the equator, in the Pacific, somewhat in the Atlantic too, they are always having nutrients because there is a region where water, because of the wind and the rotation of the Earth, are pushing the water from subsurface to the surface, bringing these nutrients continuously in the surface. Actually, when happen an El Niño phenomena, this is somewhat stopped. So you see an anomaly here in temperature. So here is also cold because of this subsurface water that is brought up. It's cold, and you see less life, and a fisherman fish less. But this is a phenomena that is a coupled system that is somewhat changing also with climate change, but it's a coupled system of ocean and atmosphere, and Michael is one of the experts that has worked on that. So here is an animation of snapshots of this sea surface height, And what you see, so here you have this Southern Ocean and the Arctic, where water is cold, so the sea level is low. And here, where it's warmer in this region, is pretty high. But what you see is that it's not really flat or a large-scale hill, but there are motion that is kind of spot that have 100 kilometers, from 50 to 100 kilometers, or 150, and these are eddies, vortex. So the ocean is turbulent and is filled by vortex, and of both sides, cyclonic, that is in the northern hemisphere, circulating, the velocity circulating anti-clockwise, and anticyclonic, it is circulating clockwise. So if we put some of this observation all together, we can, if I'm able to change transparency, we can see, so this is the sea surface temperature together with the velocity we can derive from these sea surface heights from the first order of equilibrium in the ocean that is called the geostrophy, is the pressure gradient and the Coriolis force. And so we can derive the velocity. So you see the signet of the velocity. You can see really very well the motion of the Gulf Stream, how it is, how it leaves the margin of the American continent, and here is the North Atlantic Drift, and here you see the Canary currents. But what you see most is, except in the tropics, in the equator, where the dynamics is different, you see a lot of eddies everywhere. But still, we are limited by the resolution of these observations that have increased in time, but are not completely perfect to see all the cascade of scales. So here are some snapshots of sea surface temperature. Here is the sea ice that is drifting with the ocean current in Alaska. And here is phytoplankton bloom. This is a zoom here in this region that has been taken by a Landsat images in the visible with false color. So you see that there are a lot of many scales than just these eddies that are 100 kilometer large. And this is our problem. We can hardly observe that and still at the sea surface, and we cannot really investigate that with equation unless we use models, but the models are limited by the capacity of integration in the computer, so I will come back on that. So it is a problem. Another problem we have is what I've told you till now, is that the ocean is impermeable, opaque to electromagnetic radiation. So the last spectrum length is absorbed between 10 and 100 meter depth, is the blue when you don't have organic matter, and this is it. So from satellite, we are really observing just what is at the surface. So we need to understand what is happening inside the ocean. We need to go with means in the ocean and observe. And so here is the problem. So one day of an oceanographic cruise is around 35,000 euro. So it's very expensive. So to go from this kind of ships till with a particular instrument that, for example, here is what we call the CTDs, that has automatic sensor for pressure, salinity, oxygen, and temperature. And we are developing also some other sensor for biogeochemistry. Otherwise, we have bottles that are filled at different depths to analyze whatever we are not able to measure with sensors. So we need, for 3,500 meters, that is the mean depth of the ocean, it takes about 4 hours of stations. So the cost is huge and is really time demanding. And I will show you that, however, we need to measure the ocean, because there is the challenge for our future capacity to forecast what is happening in our climate system. So this is because an oceanographic cruise is very expensive. What have done the oceanographer have tried to implement some very easy to deploy instrument that measure just temperature and that, that are able to measure temperature till about 700 depth. They cost 100 euros, so it is possible to buy many of them and try to put on oceanographic cruises, but also on commercial ships. So this is a snapshot of all the measures of the ocean temperature till 700 meters from this kind of devices. And this is for the year 1998. And so there are not everywhere, and the southern hemisphere is pretty empty. So what oceanographers have developed is another system that is robotic. It's a float that is able to go at depth, so it goes till 2,000 meters. And every 10 days, well, actually, when deployed, it stays at 1,000 meters. And every 10 days, it goes to 2,000 meters and going up, it measures temperature, salinity, pressure, now also oxygen and also some other parameters for biogeochemistry budgets. Then it goes at the sea surface, it transmits to the satellite the data that goes on land, on the data center, and then it goes at depth again, and it drifts with the ocean currents. This way, we were able to feel much better the ocean with subsurface observations. So this was when it started in 2003. That was starting to have a global coverage, and this is what I recollect from was Tuesday. So we have almost 4,000 floats into the water. But this is a huge effort. This is also, every measure in the ocean is pushed by a single PI or a single group. So to maintain this network that now has more or less 15 years of life, because this float stays there between 3 to 5 years, so you need to supply every year a number of floats and to deploy in different regions of the ocean. It's really a huge battle because countries prefer to, I don't know, to go on Mars, Jupiter, and less to observe our planet because it's less sexy. But still, it is very important. Okay, I'm passionate, but it's really important. So, what is there? So also we have developed other type of observations. So these are the ocean cruises. This is the CTD. This is the device to launch the expandable thermobarometer, so the one that measures temperature. And here are the new robots. So together with satellite and floats, we have gliders, surface gliders and deep gliders. So like in the air, we put in the water, and they measure down now to 1,000 meters, maybe in the future down to 3,000 meters, temperature, salinity, and other variables. And also we have instrumented some animals, mammifers, that are going where all these instruments are not able to go. For example, under the sea ice. So, and altogether we start to have a very nice data set. So now the ocean looks more like that. So we have system of moorings that are also, these have been put in the Pacific in the 90s to try to forecast El Niño, because El Niño was causing problems in South America fisheries, but also huge problems in climate extremes in the United States. So the Americans have pushed to have a forecast system to have at least 1 year in advance the correct forecast. It is hard because it's a very nonlinear system. It's very hard to forecast, but they were able to forecast a few months in advance. And so the rest is less organized. This is our problem because we cannot measure everything everywhere. We need to rationalize what we measure and especially to agree internationally how we separate the different tasks. So I go back now to the to the ocean. And thanks to this different kind of observation, we were able to assess where most of the heat due to human activity is gone. It's gone essentially in the ocean. This is the heat content of the ocean, so energy in joules, in zeta joules, so 10 times 10 exponential 22. And these are the other, I lost that. Where is it? Well, these are the other two components, land atmosphere, and there is also the sea ice. So you see there is almost nothing in the other components. Everything has gone more than 90% in the ocean. The ocean is warming. And where is warming? This is where it's warming. So you have the first 300 meters here of the ocean is taking up a lot of energy, but also the deep ocean is getting warmer. So, and how it happens, where it will go, because the ocean circulation, as I said, is a loop, a long loop. It can take 100 of years, 1,000 of years, but sometimes this heat that is in the deep ocean or in the subsurface will come up at the atmosphere, near the atmosphere and release it again to the atmosphere. So what are the consequences of this heating? Well, climate change has caused sea level rise. So these are the observations since the end of the 19th century to 2010. And here, so these have been derived by tide gauges that are some of them here. So they are really near the continent. But since 92, we have satellite altimetry, sea level height measures. And so we have here this zoom for this last period. And we see that from the initial period of time of measures, the increase in sea level rise has doubled almost. So global warming is accelerating now and is causing this increase in sea level rise. Sea level rise, however, is not uniform, and this is the trend over 93, 2013. So you see that there are reasons where the sea level rise is higher, and other region where the sea level height is lower. And this is essentially due to the ocean circulation that accumulates water in some regions, essentially warm water. And so we can also do the budget from where comes the origin of the sea level rise. So the highest portion is due to the continental ice melting. So water is passing from the continent to the ocean, but also from the ocean warming, because a warmer ocean is dilating. So more or less 35% today of the increase in sea level is due to this warming of the ocean. And also we have a part of error, 10%, we don't know really from where it comes from. And also we have an increased pumping of water that human activity is pumping more water that is usually stored on land, and it goes at the end into the ocean. And if we do the budget of this different part very independently due to increase, so 2 millimeters per year is due to the continental ice melt, and more or less 1 millimeter per year is due to this thermal expansion of the ocean. And compared to the rest of the continent, so we can refine again the heat that has been absorbed by the oceans is 0.72 watt per meter square, plus minus uncertainties, but it's huge compared to what has been stored in the atmosphere and continent sea ice and in the land ice down there. So the ocean is really changing, it's due to that. Another point, so in observation, so with Argo, we are now reaching 2,000 meters, but we are not going deeper than that. And if we want to measure deep currents, what has been called the conveyor belt or the thermal circulation in the Day After Tomorrow movie, so something is much slower than what has been said in the movie, that it was changing in one day. But one of the regions where we need to measure such currents, that is bringing it from the southern hemisphere to the northern hemisphere and finally to the Arctic, is the passage south of Africa, between Africa and America. And to do that in a very efficient manner, we use some deep bottom moorings that are measuring the time the acoustic signal goes from the mooring up to the surface and coming down. And this is an integrated measures of the thermoline structure, so temperature, salinity over pressure, vertically, and with difference from the eastern and western side of the basin, we can measure how much water is passing through. So, namely, we are measuring this flow in red and this flow in blue, where the yellow line is. And so this is the measure that we are doing. So there was a test period at the beginning of at the end of 2009, and now we are continuing this time series. But already from the mean between the two periods has changed. It has passed from 21 sverdrup. So one sverdrup is all the river of the globe taken together. So 21 sverdrup is 21 all river of the globe taken together. So 10⁻⁶ meter cube second -1. And so there is a change that is also observed in the North Atlantic. So the question is this due to a change in climate, a change in equilibrium between the north and south hemisphere in the ocean, or is just natural variability? This is what we do not know, but what has been really surprising, these kind of measures in the North Atlantic and here, is the very high frequency variability. So we have changes in transport that are huge. We can pass around 50 sverdrup in 1 week to a few sverdrup the week after. So this very high frequency variability in the deep ocean is really unexplained for the moment. And so this is one of the questions we are trying to understand together with the lower frequency variability. So one reason that can make this kind of transport varying are the eddies in the ocean. So eddies, we can point them in images by fingers, but it's not very quantitative. So we have developed, so it has taken a few years, but we have developed an automatic detection and tracking algorithm that we apply to the sea level fields from satellite. And so this is a snapshot. Whatever is red is an anticyclone. Whatever is blue here is a cyclone. So you see that except from the tropics, the Atlantic Ocean is really filled by eddies everywhere. And these are the eddies that this kind of instrument can see. Probably there are much higher, smaller eddies that we are not able to detect from this field yet. But so we can try to study the interaction among these eddies and the general circulation, the smooth circulation that I was showing you. So we are at the sea surface, and these are the number of eddies that pass through 1 grid cells, that is 1 degree by 1 degree, in this 15 years of data. And so you see here a huge amount of eddies that goes, up here, south of Africa and cross all the basin. You see also eddies, I lost the thing. It's very small. There is no kind of stick. Doesn't matter. So you see there some kind of road of eddies that is finishing up in the Gulf Stream. So this is just the detection, anticyclone and cyclone on the other side. Most of them flow westward. And so we are studying characteristics to try to determine the role of these eddies.
How deep?
So it depends. So in this region, they can be 1,000, 1,500 deep. And this is just the surface. We don't know really very much what is happening inside the ocean. But this is, we know because we have some sampling that is casual. And now that we have this technique, we can go really with near real-time data to each eddies when we have ships. I will show that. So this is, for example, the trajectories of this route that is connecting South Africa to the American continent. And this is a particular region because this is one of the hot topic region connecting this very global circulation that I show you in a scheme, bringing water from the Indian Ocean, that is warm and salty, into the South Atlantic. And this warm and salt water is given, so it's transported, it's transferred to the South Atlantic and then to the North Atlantic, explaining this transfer of heat from the southern hemisphere to the northern hemisphere. And they participate into this global ocean circulation. This region is changing actually. So we need to understand how this communication of heat and salt and other properties is changing. And so for that, we need to reconstruct from observations the structures of this eddy, the 3D structures and their properties and how they change. So this is a first diagnostic to understand the dynamics. And actually, in this new detection algorithm, we are able to see also the merging and the splitting of these eddies. And so we see that most of the eddies that are created south of Africa, where it's red over there, are also disappearing from the satellite in this region. And most of people think that they are just dissipating, but actually they are subducting. They are cooled by the atmosphere, becoming denser, and so they are going into a region that is warmer. So they are just entering the interior of the ocean, and we are losing their signal from the surface. They are also interacting with the huge topography that are there in gray. And so this is also something that we need to understand. But putting together, so taking, for example, this automatic detection, we can try to also go with a ship over each eddy. So this is a map of altimetry with pink dot is an anticyclone, yellow dot are cyclones. We had a ship. We were able to flow through these dots and measure the upper part of these eddies. And up there, you see that there are kind of this is density, so you see that are homogeneous in density over a huge layer. These are what is called the mode water. It is important because heat is stored in these mode water layers, and it is transported and then released in the Atlantic Ocean. So to try to do a more quantitative work, we are using now the Argo data together with this altimetry data set of eddies, and we are collocating Argo float and eddies. So we are paying attention that the Argo float, when it comes up, it is really in the center of the eddies and not lateral, because otherwise we have the vertical structure is very different at the center compared to what is in the outside part. So we have defined what is a current eddies. Is the red lines, is where the maximum velocity is. And so we take only the Argo floats that are arriving in the center. And this way we are able to evaluate the temperature and salinity anomaly and density for an eddy of this region. This is for the, and also the salt and heat content they transport compared to what is outside. So they are very salty and they are very warm compared to what is outside the eddy, so the Atlantic water. So they are really transporting a huge amount of heat and salt. So before finishing this talk, I'm a little bit late. So I talk a second about modeling. So in order to to use the equation of fluid dynamics for the ocean in models. We cannot use the full, complete simulation, but we have to do some simplifications. And so these simplifications are usually called the ocean primitive equation that we discretize over the sphere. So sometimes when the models are coupled to the atmosphere, they have two models that are interacting. But I will talk just about ocean models. And when you have an ocean models, you can do things that you cannot do in reality. For example, you can put particles in the water, if it works. No, it doesn't work. Sorry, I have to go over there. Particle in the water, and so the color is the depth, and here is the times. So these are many years. We are 400, 500 years of time it takes for this particle of water doing all the tour at one time. At one moment, it will restart. So what you see is this water is leaving the Indian Ocean, going to the Atlantic, going to the Arctic. While it's traveling in the Arctic, it's getting cooler, so deeper. Then it goes into the Labrador Sea, even deeper. And then it's coming down as a deep water, flowing 2 or 3 times around Antarctica, entering the Pacific, and then it's going back to the Indian Ocean. Stopped. And if we use millions of these particles, we can reconstruct what is the model global circulation. And so we reach to another schematics that is a little bit more complex, but still schematic, using models and data. And so this is what we were trying to measure with our moorings. So we can try to understand from models that are not reality, but well, an approximation of reality, something about the dynamics of the ocean. Of course, these models were the kind of models are used for the IPCC report are pretty low resolution. We have global models that are high resolution that we call eddy permitting, so they are able to create eddies. But the eddies are pretty slow and not very dynamic. And so we need to understand with models really what we cannot do really with nature because we cannot observe it. So to increase this resolution to try to see if we have some process we are missing in observations. And for that, this is what I show you from a global ocean models. And this is the circulation we start to have. This is relative vorticity at the sea surface. So you see eddies going in one sense, the others, dipoles. So it's really dynamics. It's 1/12 of degree. 1/12 of degree is the highest resolution we are using now for global models, but still it's not sufficient to understand some process that we observe and all the cascade of energy that exist in the ocean. So to do that, we need to go to smaller scale, and so we can do that in very small regions, academic or in this realistic configuration, and try to understand what is the difference when we have higher, well, smaller scale, so high resolution simulation, what is the difference in the physics of the process. And I will be going inside the ocean. So here I have a 1/12 degree here, that is zoom, where there is a zoom here, 136 degree of resolution, and here we are less than 1 kilometer in this small box. Here is the South Africa, so this is the warm current leaving these eddies going to the Atlantic Ocean. And this is sea surface temperature. This is the relative vorticity. So what you see here is are scales that you don't see here. Here you have really a cascade of vorticity going towards really the small scale. And this happens to be really important. So here I compare two vertical section of the stratification for 1/24 of degree in winter, this is summer, and this is 108 of degree. So you see here a mixed layer depth that in winter is less. Mixed layer depth is where the ocean transfer heat momentum to the, the atmosphere transfer. There is an interaction between ocean and atmosphere happens here. And so at 124 degrees, that is much higher than what is the global resolution of some models today, is not enough deep, while it gets much deeper with the same forcing at much higher resolution. And also in summer, when stratification happens, what is the memories of these the winter mixed layers is not really representative in this model, while really we find this mode water, we have measures at this resolution. And also in the deep, much deeper ocean happens something different. So here are the spectra for summer, winter. The surface is in dots, and at 1,000 meters we have continuous lines. So what we see is that even if it is less energetic at depth, we have a really small scales also at depth, and these are very important because they mix properties of water, of different water masses, due to the very small frontal system that get unstable in this region. So here I show you the temperature, that must be salinity, these two kind of resolutions, so 24th and 106. And here you see that there are really small fronts in temperature and salinity, but at the same density. This means that this water, because the motion is essentially isopycnal in the ocean and the atmosphere, they are really able to mix together very easily at this depth. And this is what we call spiciness, the measure of this in this kind of simulation. So here is vertical, is the sections of this spiciness. You see this layer, very important, where properties are exchanged, mixed, and homogenized during the advection. Here is an eddy, so this is at the base of this eddy that is around 800 meters. So these processes at small scale are very important. They are not for the moment in the global model for the climate. And what we are trying to understand now in our lab is also how this scale interact with the atmosphere, because while in the tropics the interaction between the ocean and the atmosphere are at a very large scale, at mid and high latitude they are at very small scale. So we need to understand how this happens, and I will close here saying that the ocean is the really essential component of our climate, because in many reasons, but in terms of changing climate, is really reabsorbing the essential of heat that is due to the anthropic actions. We have seen many signals. So we are seeing that the ocean in the climate is warming at a higher rate than in the preceding record. 30% of the warming occurs in the deep oceans, and sometimes we have a natural variability, including volcanic eruption or El Niño. In the last 2 years, there was a Niño event, so the temperature was even higher than what could have been without this phenomena. And the increasing disparity of warming in different layers are essentially in the Earth-sea interaction, but we still need to understand really well and model them. And so we have two major challenges in order to predict and to be able to adapt to climate change, is to better organize internationally a fit-for-purpose sustained observing system of the ocean and the atmosphere, and continue to work on the diversity of approach in modeling to try to parameterize the small-scale processes that are not yet well parameterized in climate models. Thank you.
I heard various things. One of them is that the climate change is amplifying the extreme events So what about the instabilities like El Nino you mentioned? We heard recently that the frequency and amplitude of El Nino might be increasing. Is that real? Is that perhaps possible, predicted, or totally wrong? What do you think?
Well, El Nino is a nonlinear event. It's true that in the last 3 years we had the 3 El Nino, while before they were lower in amplitude and less frequent in these 3 episodes, but we cannot do statistics on this way. So this is really a short time record, and I don't know if in actual climate model we can assess something about El Nino because of their resolution. But I'm sure that Michael have his own idea about that. But I think the major thought is that everything is changing, and the energy, there is more energy in the systems, and one of the energy exchange between the ocean and the atmosphere is this El Nino ENSO event, that is the highest in terms of amplitude of all the mode of interannual variability of the ocean atmosphere. So it is plausible. Maybe Michael will do a seminar one day on that. Yeah.
There's a huge literature on just trying to distinguish natural variability from forced change. And there's a lot of work, but there isn't really a proper framework for thinking even about that. I mean, there exists, I think, but it hasn't, percolated into the wider literature. And that is there are various ways of thinking about it, but one is non-autonomous dynamical systems, okay, that include not the usual ones with fixed coefficients and forcing, but variable, and the pullback and random attractors that go with those, and things like that have been started. In the case of El Nino specifically, it's not even clear, since the tropical Pacific is such a large fraction of the surface of the Earth, whether, it is what is natural variability and what is forced, and what is El Nino and what is global warming.
So the attribution of extreme events, I think, is one of the biggest challenge we have.
Very simple question. The energy budget was precise to 6 digits. When you showed it in the second or third slide, you showed that all the numbers that you showed were extremely precise.
Yeah.
How is it possible to have such a because this is the motor of all
course.
come later.
This is from different sources of different data, from satellite and in situ data in the atmosphere, in this surface level. So these are global budget that have errors, and in brackets there were the uncertainties, so the maximum minimum. So I gave brackets too. And of course there is also variability because there is sunspots or whatever, so there is natural variability too. These are schematics, so it usually are very rounded.
It's about the conveyor belt. There have been hypotheses about the possibility that the conveyor belt could have an abrupt change. But if from your argument about the fact that there's a large width of currents between the Atlantic and the Arctic Ocean, then this would fix the conveyor belt. What's your opinion about?
Well, it depends on the formation rate of deep water in the Arctic Ocean and Labrador Sea, and what is happening in the Southern Ocean, because this is not just the surface water or deep waters, there are also intermediate waters. But so this is why it's still nonlinear, because we have seen this huge variability we observe. So this is why nobody is able to say that it's diminishing or not. But this is why we need long records to understand what is natural variability and what can be the circulation. So the circulation is just buoyancy forcing that mix with wind forcing, but they are not so connected straightforward. So we don't know really. For in the mean is 18 Sverdrup, but as you've seen, I can go up to 50 and down to in a few days. So.
Like here, say, including the development of new observing technology. Do you have already ideas of what they should do?
Well, all the technology that have been developed are always coming from researchers working with engineers first, like the Argo floats. And so we need to try to go deep in the ocean. Gliders, for the moment, are very beautiful, but they have to be, must always be one person to know if the glider is doing well. So it's very heavy to implement. And Argo float, for example, for the moment is going to 2,000 meters, is not going up on the slopes, while most of the currents are really on the margin of the continents. So we are measuring half of it. And these gliders can go there, but they are so heavy to handle that it's not so easy to bring them everywhere. And also to measure whatever is not measured automatically today. So for example, the other problem for the ocean is absorbing 1/3 of the CO2 emitted by the human activity. And this is changing also the pH of the ocean. And so all this biogeochemistry equilibrium need to be monitored. And for that, we cannot always go with ships collecting the water and analyze. So other sensors measuring pH, alkalinity, or other variables are needed for that, together with radiation observations too.
One last question.
Okay, I have two questions. From mesoscale to small scale, what is the, in terms of kilometers? What is the range of?
So mesoscale in the ocean is about, it depends on the latitude, but it can go from 20 to 200 kilometers in diameter. And what is less than these scales, so going down to 100 meters, is submesoscale. And submesoscales is originating from instabilities of the mesoscale.
Now, the second question is, when we are looking for new parameters, for the present time, how many parameters we already know?
The parameter in these terms, so developing of parameterization for modeling?
Yes.
Well, there are some, the problem is that for the moment, what is subgrid? So what is smaller than a grid of the model, we just put something constant proportional to something else in terms of diffusivity or diffusion, etc. So we need to have a more sophisticated parameterization taking into account a dynamics that is not proportional just to a constant and something else. It's depending on the dynamic itself and the forcing of the system.
Thank you very much again, Professor Sabrina Speich.